We just have to write stop at the end.
All right. How do I, might as well just share window then. This is like a very strange time to have my machine not allowing me to share a window, to share the full screen. Okay, so I think I'll just share a window, and then when I'm done with the other chapter, go to the other one. 12. Please let me know when you can see my screen.
Okay, just loading up for me. It says for me at least that you've started screen sharing, but I don't see the screen.
It doesn't show the screen.
Oh, there we go. I've got it now.
Yeah.
Oh, so you both can see the screen.
I can, yes.
Perfect. All right. Yeah, so today I'll be taking us through chapter 12 and 13. Chapter 12 is on visualizing associations among two or more quantitative variables. As I was going through it, it felt quite long, so hopefully we do get to cover both chapter 12 and 13, but I suspect it won't be as long now than when I was going through it. All right, so generally when we have two quantitative variables, we tend to use scatter plots, which is what the author also went for. So I'm just providing here some info that is used for most of the plots that we'll be looking at. And it's basically a data set of measurements performed on 123 blue jay beds. And we'll mainly be looking at the head length, which is measured from the tip of the bill to the back of the head, and then the skull size, which is the head length minus the bill length, and the body mass of each bed. So the idea is that there are relationships between these variables, and we want to investigate them. All right, so the first plot is we want to look at head length against body mass, and standard procedure, we just do a scatter plot. Something that I found interesting was this note on terminology, where he says, we say that we plot the variable on the y-axis against the variable on the x-axis. I feel like this is something that somehow intuitively I've just always assumed, but I think it was quite pleasing to see it noted out. But yeah, so we've got a simple scatter plot here with our head length against the body mass. But then if we want to check if the relationship between the head length against the body mass holds separately for each sex, we can introduce the sex of the beds. And that is done by just mapping sex to color. So we've got the male beds in blue and the female beds in orange. And yeah, even though it's not like super strong, you can see there that generally male beds tend to have longer head length compared to the female beds. Yeah, please do let me know if I'm going too fast or if I'm not audible, because now that I've shared my screen, I cannot really see the chat or even the faces.
Yeah. No worries. You're sounding good and pace is good for me so far.
Fantastic. All right. Yeah, so far, nothing hectic. I think it's stuff that we probably all have engaged with. And then if we wanted to introduce another variable, in this case, skull size, so the author then said we can just map skull size to the size of the points. And that's how we get our bubble chart. And general bubble charts are scatter plots with the size of the dots being mapped to some other variable in the data set. So here the author actually points out like some challenges with this. One being the differences in the sizes of the circles they're kind of hard to notice. So for example, yeah, literally, even though there's some difference, it's practically impossible, not impossible, but really hard to see. So I think he makes a point there that it is difficult to determine what the relationship is between skull size and either body mass and head length. So to address that, he says you'd rather plot an all against all scatter plot matrix. Yeah, I think I'm generally used to this being called like a pairwise scatter plots, which he did eventually write as well. So here, rather than having something like this, for example, we've got head length, body mass, and skull size, and then the same variables on the x-axis, and that's how we get the matrix. And of course, the diagonals are just the same variable against itself. Yeah, so the point that was made in the book here is that because we are better at judging position rather than symbol size, it's much easier to see the relationships here. Like, for example, you can see here skull size with body mass. You can't really say between male and females, they're kind of comparable. However, if you look at head length and body mass, you can see that males tend to have larger head length, longer head length compared to females, which was, yeah, but I guess, yeah, that is actually quite clear. Whereas here with skull size and body mass, they're kind of comparable. Yeah, I think in my experiences, plots like this I've generally done when I'm doing exploratory data analysis just before fitting a model. I've never done a plot like this in communication, and I think that's probably the case with most people. All right, so I should point out this is one of two slides that are text heavy. I've tried to not make them super text heavy, but yeah, I thought there was a number of things that I needed to point out, and I was sure that I will forget them if I don't write them down. So when we have more than 3 to 4 quantitative variables, all against all scatter plot essentially becomes unusable. In this case, the author then suggests that it is more useful to quantify the amount of association between the pairs of variables and visualize this quantity rather than the raw data. And the common way of doing this is to calculate the correlation coefficients. And yeah, visualizations of correlation coefficients are called correlograms. I do apologize for a text-heavy slide, but I just needed to get that theory out of the way. Right. So an example of this is with a plot like this. So here we've got 214 samples of class fragments. And for each fragment, we kind of look at the mineral composition of each, and we've got the different minerals there. So rather than plotting the actual raw numbers of the minerals, what we've got here is rather the correlation between the minerals. And I think some relationships start to just stand out. You can see the magnesium is literally negatively correlated with most of the other minerals. And then you've got aluminum there being positively correlated with, I think it's barium. Yeah, this was quite interesting. This is also another plot that I don't think I've done too many of. Yeah, I think as far as I tend to go is with the pairwise scatter plot matrix. But yeah, I thought this was interesting. However, the author did point out that with this, so basically it's hard to see kind of, if you check here, magnesium and potassium aren't really like highly correlated. There's practically no correlation between the two, but with this type of plot, it's kind of hard to see them. And to then kind of make that quite clear, he suggests you then kind of map the correlation to the size of the point, which I thought is interesting because just not long ago we had an issue by using size here, the size of the dot, and in one case here, it ended up actually working quite well. Because here you can see that the correlation between magnesium and potassium is actually quite low, pretty much zero. Yeah, and that is that on correlograms. Yeah, I think this chapter, just because of how huge it was, I did try to just take the key terms. So if I'm skipping stuff, please go look at them in the book.
Just
So
one
then there
question.
was
If I
a
can ask
section.
one question, Retselisitsoe,
Oh yes, yes.
about the parallelogram. So he's mapping color to the correlation coefficient and also size to the absolute value of the correlation coefficient.
Yes, yes,
Okay.
yes. Actually, that was a good point that I don't think I emphasized that the circle is the absolute value. Yes.
Okay. I assumed it was. I just wanted to double check, but yeah, totally makes sense. I like it.
Awesome. All right, and then the next section was on dimension reduction, and the author did say you'll only focus on PCA. And yeah, generally PCA just introduces a set of new variables called principal components, and it does this by taking a linear combination of the other variables in the data, standardized to zero mean and unit variance. Yeah, I think this is also one section that it's probably best to read it in the book because it's properly explained, but I did try to just grab the key points. So when you perform PCA, we are generally interested in two pieces of information: the composition of the principal components and the location of the individual data points in the principal components. So the next two examples try to kind of address each of this. So this is the same example of the mineral composition of the class fragments. So after doing PCA, we've got our two principal components. So PC1 on the x-axis and the second component on the y-axis. And yeah, if you check PC1, you've got aluminium, barium, and what's that? And sodium and magnesium kind of, or rather, these are associated with the negative values of this principal component. I always have a hard time interpreting the principal components just because they are not actual columns. And in my head, I think I want to think of the columns in the data set. But yeah, these are just principal components. And then you can see calcium and potassium are associated with values of the second principal component. Yeah, I wasn't too sure about including this in the slides, but I was just like, it might be helpful. And then the second part is now we are projecting the original data onto the principal component space. So we still have on our axis the two components. So generally, it's not just the two components, but a huge chunk of the variation tends to be in the first two, three components. So yeah, you can see here, if you're projecting the original data onto the component space, some stuff that we match, I think this is what headlamps, you can see they're associated mainly with negative values of PC1. And then this, what are the circles? Window fragments are more associated with positive values of PC1. But then for tableware and container, those are just kind of scattered there. Yeah, to be honest, I rarely ever do any visualizations from PCA. Generally, I just do the PCA and then fit the model. So it was interesting to see the book just go deeper into like visualizing this. Yeah, and then the next section was on paired data. So this is data where there are two or more measurements of the same quantity under slightly different conditions. So like the simple examples tends to be like measuring the same person either at one point and then again at another point, or before they take some treatment and then again after some treatment. But the example that was covered in the book is CO2 emissions per person measured for 168 countries, both in 1970 and 2010. So you've got one variable on the y-axis and the other on the x-axis, and then this line here is basically where x is equals to y, and the idea is that if there's no kind of systematic relationship, then there will be like just symmetrically laying along the this diagonal line, basically where x is equals to y. However, if you can check here, the data is systematically on top here, which would suggest that for most countries, their CO2 emissions have increased from 1970 to 2010. Yeah, this is another plot that I don't think I use a lot, but it was good to come across. And then he points out that if we have a smaller number of observations and we are primarily interested in the identity of each individual cases, so here we are not interested in the general trend. Like here, what this emphasized was basically just generally how have the emissions changed from 1970 to 2010. But then with like a slope curve, we have like a chance to go to basically focus on the specific countries, for example. Yeah, and I think this needs no explanation. Basically, you've got the CO2 emissions 2000 and then again in 2010. Yeah. And then he says with the slope curve, we can compare more than 2 measurements at a time. So you can see that we're still looking at CO2 emissions over time, but rather than just at 2 time points, we can look at, say, 2000, 2005, and 2010. He does note that this now does start to look like a normal line graph. But I would imagine if it was like over a couple more years, then you just stick with the line graph. But because it is just like about 3 years, then a slope curve still makes sense. Yeah, and I think in the book, he points out, like, for example, you can see like Qatar from 2000 to 2005, they were increasing, and then from 2005 to 2010, there was like a huge decrease there. All right, and I think that was that on slope curves. Yeah, and funny enough, that's the last part on chapter 12. Before I go to chapter 13, are there any questions? I think, as I said, I've tried to kind of keep it visual and then leave most of the text. So some things that I'm not going into by just going through the chapter in the book, you might get the context, but are there any questions before I go to chapter 3?
None for me.
Ah, fantastic. I think I see why when people are presenting, they don't, because you can't really see the chat or anything. Okay, so I'm just gonna stop sharing and then open the second window just because it didn't allow me to share. So I believe tab 13. All right, please let me know when you can see. Can you see chapter 13?
Yeah.
Ah, fantastic. Yeah. So chapter 13, visualizing time series and other functions of an independent variable. This was an interesting chapter because I saw a bunch of plots that I have never used. So yeah, the first one, I guess this is like a standard thing that we know, but the example that he uses is a pattern of monthly preprint submissions to like a biology server. And the key points that he highlights are that, because I mean, it looks like a standard scatter plot, except the dots are spaced evenly along the x-axis and there is a defined order among them. Because for all intents and purposes, you kind of do have two variables, the preprints per month and the year on the x-axis. But then the fact that the dots are evenly spaced along the x-axis and there is a defined order makes it different. Yeah, so he says here we can visually emphasize the order by connecting the neighboring points, and I am pleased to tell everybody that this is called a line graph. He also says that you can literally just remove the dots and just keep the line as it is, and it yeah, I never know if there are any rules about when to keep the dots and when to not keep the dots, because I know some people can get very animated about connecting the dots, especially because it implies that between the two points that there is data. But yeah, there wasn't a discussion on it in this book, but like I know it's a thing that people can really get into. All right, and then he says we can further emphasize the trend in the data by filling the area under the curve with a solid color. And quite frankly, if I compare the two, this one with the solid color does emphasize the trend, at least for me. Yeah, and there wasn't really much on individual time series. And then he talks about multiple time series and those responses. So here we are not just looking at preprints for one server. There are three kind of servers. So he says this figure is labeled bad because the three time courses usually interfere with each other. Like, I don't think people will draw plots like this, but I think he was just trying to make a point. So even for here, you just connect the dots with a line. So essentially you've got three line graphs, each one for the particular server. But he further says we can improve on this, just make it visually less, the user doesn't have to work too hard. And one of the ways to do that is to remove the legend and also remove the dots. So he says, by direct labeling the lines instead of providing a legend, we have reduced the cognitive load required to read the figure. And quite frankly, if you look at the two plots, this one is much easier on the eye. Yeah. Yeah, and that was that on the multiple time series and those response curves. Yeah, and then there was this section which I just had to reread a bunch of times because it just seemed strange. So he says here we've got time series of two or more response variables, and then the example that was used was, say, we wanted to look at change in house prices from the previous 12 months as it relates to unemployment rate. So he says you might start by plotting the two time series side by side like this. However, it's hard to kind of see how they change together. And then the suggestion to improve on that was to plot this connected scatter plot, which I don't think I've seen this plot anywhere. I haven't used it myself either, but generally how it works is that you've got you still have the time component, but also you've got the direction of how things go. So for example, the way he did it here is the kind of late years are lighter, and then the more recent years are darker. So you can see there it starts off being light, and then it keeps and becomes darker as the years increase. So he also says that one way that you can indicate direction is by including, say, some arrows on the plot. I can imagine that might clutter the thing, but it doesn't really have to be too many arrows. I think 2 or 3, just so that the person can see how to follow the chart. Yeah, like I said, this is one plot that I am not too familiar with, and I think he does say in the book that research says that people tend to misinterpret these types of plots. However, they do have some advantages over, say, line plots like this, because he says here, if you look at this there's this small circle and this bigger kind of small circle, they indicate like the cyclical nature of the relationship between the two variables, which is not really easy to see with these ones. Yeah, like I tried to look at this a number of times, and I still, I don't know if I would prefer or use this plot. I don't know if anyone between the two of you have encountered it before, but I think he said physicists and engineers, they come up in their work. I was like, okay, maybe it's like very domain specific.
I've never seen this graph before either. And I actually didn't make it this far in the book for this week's reading. So this is all new to me. I'm intrigued though. If you go back to the previous graph, maybe you two
This
can help
one.
me understand. Yeah, so if I was to look at this graph, I might say, oh, in across the, I don't know, 15 years or so in this data set, in 2005, the 12-month change in house prices, the first graph, was high. And
Mm,
in 2005, the same year, the unemployment rate was low.
yes, yes.
In the next graph, where do I look to like get that kind of insight? Do you know? Like
Yeah, I would imagine it's because I feel like it 2005, 2010, 2015. Because I also tried to figure out how would how would it how would it but I suppose one thing you can tell is that, say, I'm assuming this is 2000, right?
oh, I
Because
think
it's
I
like,
understand it now. So it's January 2005 is in the top left corner with the label.
yeah, so then the beginning will be
So
somewhere here.
yeah, so if it's up in the top left corner of the graph, that means high
Housing.
y-axis as it always does, I guess, and low
Yeah,
x-axis again, as I guess as it always does. So on this graph, there was no time. There's like no data in the top right corner, meaning there's no time where over this 15-year period, the unemployment rate was high and the 12-month change in housing prices was high.
yes, yes.
Um, it's mostly in the top left where, well, maybe not mostly in the top left. I guess it did do a big cycle.
Mhm.
Okay. I think I have a bit more intuition now about how to read it, but thanks for helping me walk myself through it.
You're welcome. I felt like I didn't do too much, but I'm happy that I will take any form of credit.
Sounds good.
All right. So yeah, besides this, he then says that even though connected scatter plots can show only two variables at a time, we can also use them to visualize higher dimensional data sets by applying dimension reduction. And again, this is an example that uses PCA. I think because this plot, oh yeah, I won't be able to open it in another tab because I'm sharing this window. But so for example here, we've got, I'm assuming the data set had over 100 microeconomic indicators from 1990 to December 2017, right? So, yeah, I think it's important to note here that this is on the PCA space, not on the XY coordinate system. So if you plot the data set on the PCA on the PCA space, you I mean, this one does look almost like a normal line graph, even though it is not. But we can see, for example, that the change is mainly, actually, wait, let me not start making stuff like that. But we've introduced more variables in the sense that now we have recession recovery with color, but then we still have the direction and the time component captured as well. Yeah, I think this connected scatter plots, I was seeing them here, and I probably I'll have to go over the section again just to get them, because I would imagine they are instances where they are helpful. Um, like here, as the author pointed out, I think he said, where is it in the book? Because I think he said you can see that PC2, for example, is associated with like the overall kind of economic change. Yeah, but I guess it's not as intuitive, and I doubt that this is a graph that would be made for communication. It's probably a graph that would be used in like EDA. Um, yeah, and I think this is pretty much it. Funny enough, I was worried that the other chapter was long and I might not even get to cover this one, but I seem to still have plenty of time left. I don't know if there are any questions.
More a comment on this last slide you have up. A graph that combines PCA and like a connected scatter plot like this. It's really tough to understand. I have no idea what this is trying to tell
It
me.
is, to be honest, like it really is. Because I feel like even if you do point out some insight, it's going to be hard to communicate because the other person still has to do the work to see that insight.
Yeah.
And in the book, the author does tell you what the insight is, but then you try to look at the graph and understand, and it's quite challenging.
Mhm.
Yeah. But I think he argues that he does make a point that they are not properly understood. However, he feels like if people understood them better, then they would. The main thing that he seems to emphasize with them is like the cyclical nature that they're able to show. And I think with this second plot here, PC2 and the third component, it's supposed to highlight the cyclicality quite well. But yeah, no, I read this so many times and I was still having a hard time with it. But I kept it in the slides just so that, in case someone has experience with them, then they can just tell us more about them.
No, for sure. That sounds wise.
Yeah, that's pretty much it. And I think if there are no questions, I would imagine everybody would be happy to call it a day.
I think so. No questions for me. Thanks so much for presenting Retselisitsoe. It's very cool stuff, and I feel like it's a level maybe more complex than like the previous chapters we've done on like bar graphs and nested proportions and like things that are relatively simple. So thanks for tackling
Yeah.
the hard chapters, so to speak.
I also think I got exposed to stuff that I generally wouldn't see in my day-to-day job. So it was quite interesting. It was quite interesting to
Okay,
read.
that's the goal, I guess, of volunteering to lead a session. You know,
Yes,
getting
especially
exposed to things you
on the
don't see.
stuff that you're not familiar with. That's
Mhm.
what makes it even more rewarding. All right, I think we can do stop and then just call it a
Yeah,
day.
I think I have to write